Friend, welcome. My name is Derek Carter, and in this video, we're going to continue our discussion about the XV6 operating system. So we're working our way up to talking about the process abstraction. At least that's what we're mostly focusing in here in our chapter 2. So actually, I didn't have a very good dividing point. This video is probably going to be relatively short. You can kind of think of this as an introduction to the next one, where we're going to dive into the boot process and talking and specifically looking at some of the details of how processes are implemented in our XV6 system. Okay, so if you're ready, let's go ahead and get started. Okay, so before we get back into the XV6 code, let me just bring up this idea of monolithic kernels versus microkernels. So in any operating system course, you're likely to see this mentioned. We probably won't see any more discussion of this in this course, but you got to be aware of it. The idea of a monolithic kernel design is where basically the entire operating system resides in the kernel. So implementations of all system calls run in supervisor mode, right? So really, the XV6 teaching operating system that we're looking at, it's an example really of a monolithic kernel design. Okay, so the original Unix, AT&T Unix versions kind of were monolithic, and then the microkernel design was a little bit of a reaction to that, trying to do some different things in order to see if that worked better or not. So, and by the way, Linux, probably the biggest, most successful kind of operating system, at least on servers and things right now, is kind of in the traditional monolithic kernel. So it would be considered a monolithic kernel. So, this has pros and cons. It makes it, the kernel code very large and complex, so it can be very hard to understand. But, just related to that, you don't have to divide your code into parts. And it's easier for different parts of the operating system to cooperate, because if they're all just part of the kernel running in supervisor mode, you don't have to do a lot of the checks and other things that you might have to do for a microkernel approach. Okay, so anyway, a microkernel aims to minimize that. So it tries to get the minimal amount of functionality as possible that's needed to be in the actual kernel that runs in kernel mode or supervisor mode. And then everything else is pulled out. Is going to run as sort of operating system services in a microkernel. Okay, so those services, the thing about a microkernel is these services will be running. They're not actually user processes or things that are started by the user. They're started by the operating system, and they're invoked from supervisor mode to do things. Okay? So in theory, if you can shrink the kernel, it makes it easier to understand the actual kernel supervisor mode code that's needed, but it tends to be a harder design, I think. So most famously, the Berkeley kernel, I believe, from which like the Mac OS, which is, I believe, what Mac OS is kind of based on. So there was these Unix operating systems from Berkeley, Next Step, and then the called Mac OS kernel, which were kind of what I usually think of as the primary examples of microkernels. Okay. So irregardless, of like a modern operating system that you might look at or think about, whether it's considered monolithic or a microkernel sort of approach to design, I mean, they are all implementing the stuff that we've talked about kind of already. Okay, the same kinds of abstractions for the most part you're going to find in Windows and in Android and Linux variants, Mac OS, things like that. So it's usually a system call API. Windows is considered a little bit more object oriented, so it's kind of like a class hierarchy. So the API, but still, it's really an API of system calls that represent a transition from user mode into kernel mode. All modern operating systems meant for general purpose use are going to implement virtual memory. So they're going to implement usually having page tables. So there'll be this abstraction called a process, and that is, each process has its own page table, so each process has its own virtual memory address space, as well as each process has one or more threads of execution, so a program counter and things associated with it. All operating systems support concurrency mechanisms. We'll talk a little bit about that in this course here, the concurrency mechanisms that are implemented in XV6 using the RISC-V hardware architecture. And the file system abstraction is pretty common. So file system and something like file descriptors for simplifying the opening and moving of data and communicating data between separate entities, and then having an easy way. So especially in the Unix family, the originator of a lot of these ideas, the file system and the file descriptors go hand in hand. So you can connect a file descriptor up to a file in the file system, so you can easily get things to and from long-term storage on hard drives. Okay. So the final thing I'll do in this video, I'm going to jump and just kind of look at the kind of high-level overview. Our textbook has this table here about the code, the organization of the XV6 code. Although there's nothing that this is all these files are in the kernel subdirectory of our XV6 source code. Okay, but we can break these up to related groups. So in the next video, we're really going through the boot process. So we're going to look at the entry, the main, and the start files. Entry is just assembly code, so RISC-V assembly code, which ends up invoking start, and start invokes main. Hopefully I didn't have that backwards there. And we're going to talk a little bit, we're mostly concentrating in this chapter, the way I think about it, on the process abstraction. So we'll look at how processes are implemented in XV6 in a little bit more detail. So that includes the process structure is defined in proc.c and proc.h, and we'll look at the exec as well and talk about the init process here. Okay, so let's look at those, the layout real quickly. So, if you're using the source code container for our XV6 operating system course, you should have an XV6 RISC-V subdirectory with a kernel and user. Okay, so all of the kernel code that gets compiled and is stuff that's actually running in kernel mode or supervisor mode is here in the kernel. A bit of an aside, so I may or may not have this, but I usually, a lot of these files are just products, like .object files, .d files, which I'm not even exactly certain what the .ds are. So these are just kind of clutter up, make it harder to find stuff in here. So I often just exclude all of those. So if you don't have something like this in your settings.json file under the .vs code, settings.json, you can add something like this, or you can find it under, I think if you go to settings, look for like exclude, you can add it here, although I don't know, this probably adds it to your global or something, not certain. But this should work. So if you put like a files.exclude, I usually just have it not show me the .ds and the .os, and under my user, the same stuff, but also all these underscores, which are the, I think these are the executable results of the user programs that are put in the file space, the root of the file space. So anyway, yeah, if I put those in there and just save it, makes it a lot cleaner. So mostly you'll just want the .c and the .h files, or the .s. There are a few others that may or may not be useful, but I'll just leave them in there for now. So mostly, I just want to see the .c and the .h files like this. Okay, and then, real quickly, so I'm not going to actually start talking about these. This will be in the next video, but, the boot files are the entry.c, so the entry.s. So whenever you have a .s, this is actually going to be RISC-V assembly code versus ASM, which is actually the result from compilation. So yeah, you don't have to worry about ASM files. So really, the .s files are the ones that get compiled into object files using the RISC-V compiler. So entry ends up calling start. So the start.c is the next thing that goes after this, and then start.c calls the main somewhere in here. So those are part of the boot process. And then if you look in here for like the exec and the proc, so proc.h, as we'll talk about in the next one, has the header file, has some structs and stuff defined. Proc.c is actually the implementation of the functions for the process. And the exec is where the exec system call is implemented. So you'll find stuff in there. But again, we'll talk about that for the next video. All right, so yeah, that's it for this video. Like I said, it's kind of short. You can kind of think of this as a prelude to the next one. So, so what we talked about in this video, we talked about the difference of monolithic versus microkernel. After taking an operating system course, especially a graduate one, you ought to kind of be aware of those terms, and also just be aware of that. Linux is kind of like Linux and the classic Unix. AT&T version, System 5, System XV6 are all kind of classic monolithic kernels. There is a movement to try and do microkernel designs, which have trade-offs, pros and cons, and things. But irregardless, there are certain common things that all operating systems, even our teaching XV6 operating system, implement. So basically some sort of an API, which usually is the transition from user mode to kernel mode. It's how user processes invoke kernel services and switch into supervisor mode in order to get things done. Page tables and virtual memories, along with the process abstraction. Organizes and is the hook for a lot of these things. So virtual memory, multi-processing, so being able to switch between processes and things like that. And then the file system abstraction is pretty common. Most operating systems have some way to make it easy to work with permanent storage. In Unix-like systems, file systems go hand in hand with file descriptors, which is kind of a streaming interface that you can connect to files, but to pretty much to anything that you can treat as a stream of bytes to get a stream of bytes to and from it for communication. Okay, doke. That's it for this video. As usual, give me feedback if you have questions or like what you see or don't like. Yeah, I hope to see you guys in class or in the next video.